Welcome back. This is the day the Lord has made. Let us rejoice and be glad in it. In this video, I'm going to talk about how to solve a variety of things to connect to circuits. Some of this will be including total resistance, so it'll be the current. We're going to solve for voltage drops. We're going to solve for power used by individual resistors as well as total power used by the circuit. So here we go. First circuit we're looking at is this resistor right here, the series circuit. We have an 18-volt battery, a 3 ohm resistor, and a 6 ohm resistor. Both the 3 ohm and the 6 ohm are in series, which means that the electrons have to travel through them. So as electrons leave the 18 volts, they're going to go through a 3 ohm resistor, then a 6 ohm resistor. So what's our total resistance? Since it's a series circuit, we're going to add those two together. 3 plus 6, we got 9 total ohms of resistance. Now, how much current do we get? The current is going to be based off of the motivation and the anti-motivation. So we have 18 volts of motivation. The voltage divided by the total resistance is going to give us the total current. So in this case here, we're going to have a total of 2 amps of current moving through. So with an 18-volt battery and 2 resistors, 1 3 and 1 6 ohm, we would end up having 2 amps leaving. Now this 2 amps is everywhere because it's a series circuit. Voltage drop at the 3 ohm resistor. So as the electrons move through the circuit, they're going to get demotivated. They're going to lose motivation as they complete a homework assignment, just like you guys do. So they have a 3 ohm homework assignment to do and a 6 ohm homework assignment to do. When they budget their strength, they're going to budget most of their energy for the 6 ohm resistor. So to find the voltage drop, you got to proportion it out based off each resistor. So in this case here, we have a total of 18 volts to spend. Now, as it goes through the whole circuit, it's going to go through a total of 9 ohms. And so, the voltage drop of that one, we're going to spend 3. So the way you calculate this is we have 3 ohms at the 3 ohm resistor. The total thing has a total of 9 ohms. So it is 1/3 of the total resistance. So we're going to get 1/3 of the total voltage being used here. 1/3 of 18 is 6 volts. Alternatively, we could have solved it another way by saying that since we have 18 volts and 9 ohms, that means that we have 18 volts per 9 ohms. That is 2 volts per ohm. So we could just say, well, for this next one, the 6 ohm, how much motivation do we lose here across the 6 ohm? Well, it's 2 volts per ohm. So 2 volts per ohm times 6 ohms means we're going to have a total of 12 volts lost there. So again, another way to double check your work on this is you should always run out of all your voltage. Again, electrons are the perfect cross-country runners. They have 18 volts of motivation. As they cross the 3 ohm resistor, they spend 6 volts. So they had 18 volts here. Now they're down to 12 volts here. Then they spend the last 12 volts going here. Now to find the power, again, power is equal to the voltage times current. However, you only get to use the voltage that you actually used, whatever voltage drop you have. So to find the 3 ohm resistor, we use its voltage drop. We have used 6 volts there. Both of them have 2 amps of current going through it. We're going to use 12 watts of energy at that location. The 6 ohm resistor is going to have a little more power generated from it because it used 12 volts in the motivation and it still got 2 amps. So it's going to do a total of 24 watts off the line there. Total power used from the line then, we'll add up all those resistors. So we have 12 watts plus 24 watts. This is going to equal 36 watts of energy being used by this circuit here. We'll do it again with another circuit. This time we have a parallel circuit. So in this circuit here, circuit C, we have a parallel section. We only have one place where we have to go through resistors. So the electrons that leave this battery only do one assignment. So we're going to spend all their motivation there. We'll get to that later. Find the total resistance of the circuit. We need to solve the way you would solve for parallel ones, since 9 and 18 are parallel. So you take 1 divided by 9 plus 1 divided by 18, and solve for 1 over x. So 1/9 plus 1/18, then 1 divided by that. In this case, your x equals 6 ohms. So if you have a 9 ohm resistor and an 18 ohm resistor in parallel, you end up having what's considered an equivalent resistance of 6 ohms. Again, as electrons leave here, they see this little parallel section, and it looks like a 6 ohm resistor. Again, it's less resistive because we have multiple options. So the 6 ohms is smaller than both of the other resistors, because we gave the students a choice what assignments they want to do, they are more open to actually completing the task. So to find the total current then, we're going to consider each one individually. So we have 12 volts. Oh, wait, sorry. The total current, we'll split that later. The total current, we'll take the 12 volts, that's our total motivation, divided by the equivalent resistance of the circuit, which is 6 ohms. That means we're going to have 2 amps. So this has the same current as the last one. Now for voltage drop, we don't need to proportion out. In the last one, we had to proportion it out because we had to save energy, save some motivation for 2 assignments. Here, the electrons that leave here, the ones that go on the top, are not going to come back and redo this assignment because once they get past the 9 ohm resistor, they're going to just finish all the way to the end, which means that both the 9 and the 18 ohm resistor are going to get 12 volts of motivation. And this is why we put things in parallel at the house so everything gets the same motivation. Now the total current is 2. That 2 amps is going to split up though. Some's going to go to the top, some's going to go to the bottom. So there's a couple ways to do this. The way we're going to do this assignment is right for here, at least in this example, is I'm going to use the voltage drop for each one and divide by the current. So it'll work out to be 2 amps. So we have 12 volts of motivation going through a 9 ohm resistor. So we take 12 volts divided by the anti-resistance. And that gets us 1 1/3 amps going through that section there. The current through the 12 volt for the 18 ohm resistor, 12 volts divided by 18 ohms. This equals 2/3 of an amp. So again, you'll see that the current split up such that twice as much went to the 9 ohm as the 18 because it's the path of less resistance, so we'll get twice as much because it was half as resistance. So the resistance and the current are inversely related here. Now to find the power, we get to use the same as last time. Power equals the voltage times the current. So the power is going to be equal to our voltage drop. Each one gets 12 volts. Going through the 9 ohm resistor, we're going to have a total of, looks like, what's that, 16 watts. And going to this one, same thing. The only thing that's different here is we have less current going through it. The 18 ohm resistor is going to draw less power off the line because had less current run through it, so it's not going to draw as much power off the line. That's 8 watts. Total power being used here then is going to be 16 plus 8. It's equals 24 watts. We could have also figured this out right from the beginning as well. So again, if you think about the total circuit in general, we have 12 volts of motivation. We have 2 amps moving. So 12 times 2 is 24 watts. Here we just divide it up amongst the different resistors. We're saying that the 9 ohm resistor is going to be doing 16 watts and the 18 resistor is going to do 8 watts. But again, we could have solved for the whole circuit right away. Could have done that up here too. 18 volts, 2 amps, 18 times 2, 36. All we do is distribute it out to different ones. One more to do, and then we'll be done for the day for this one. All right, so this time we have a parallel part and a series part. So the electrons that leave the battery are going to first make a choice to go top or the bottom here, come back together, and then go through the 3 ohms. Everyone goes through the 3 ohm. So everyone's guaranteed to hit that one. Then we got to find out what this parallel section looks like here. In the case of a parallel section where we have the same resistor, we can just divide by the number of resistors. Since we have 2 resistors, we'll take 2 divided by 2. This looks like a 1 ohm resistor. So the total resistance of the circuit is 4 ohms because everyone hits a 3 ohm resistor in series, and 1/2 plus 1/2 equals 1 ohm resistance on the parallel section. So we can treat this as if it's in series. The electrons leave here, they see 1 ohm, then they hit a 3 ohm resistor. Find the total current, we have 8 volts, we have a total of 4 ohms, got 2 amps of current leaving through this thing here. Now, to find the voltage drop for the 2 ohms, both of the 2 ohms will be the same. They're both going to use the same voltage drop, but they're not going to get the full 8 volts. Again, up here in this parallel section, we gave both of these things the same voltage. That's still going to be true down here, but we can't use the full 12. We got to spread this 8 volts amongst the 2 ohms, and they got to save some for later. So we're going to proportion out the way we did before. So the 2 ohm sections, they represent of the total resistance 1/4 of the total resistance. So they're going to get 1/4 of the total voltage. So they're going to get a 2 volt drop across right there. So going from here to here, we're going to spend 2 volts of motivation. The 3 ohm one represents 3/4 of our total motivation, or 3/4 of our total anti-motivation resistance. 8 volts, that's going to put us at 6 volts being used there. So again, back, big idea. We have a total of 8 volts to spend. We're going through a total of 4 ohms. This current here is also thought about as the amount of volts per ohm that we lose going through the resistors. So going through a 1 ohm resistor, we spend 2 volts per ohm. So we spend 2 volts of motivation going from here to there. And then from here to here, since you're spending 2 volts per ohm, that's going to be 2 times 3, 6 ohms. Now, to find the current to the 2 ohm resistor, we use the voltage drop actually across the 2 ohm resistor. Okay, so we have 2 volts of motivation, not the whole 8 volts, just 2 volts for the top, 2 volts for the bottom. So if we have 2 volts and 2 ohms, 2 volts divided by 2 ohms, that equals 1 amp. Now this is true for both of them, and we could have actually solved it differently by just saying, well, we have 2 amps leaving, and they got to split up. Since both paths are the same, it splits up evenly, with 1 amp on the top, 1 amp on the bottom. Current through the 3 ohm, this will be the total current, because it's in series, that's everybody. Everybody is going to come through here. To find the power again is just equal to voltage times current, and we only get to use the voltage drop we have there. So for the 2 ohm resistors that are in parallel, they each get 2 volts, and they have 1 amp, so that means we're going to get 2 watts from each of them. So the total power is going to be used is going to be 4 watts total from both the combined. So 2 watts from the top, 2 watts from the bottom. For the bottom one, our power, we get to use 6 volts of our motivation. We get all the amps going through there. That's going to be 12 watts. Total power used here, we have 12 watts being used by the 3 ohm resistor, plus we have 2 watts being used by one of the 2 ohm resistors, 2 watts being used by another one of the resistors. That gets us a total of 16 watts. Again, we could have solved this initially to find the total power by just saying, well, we have 8 volts, and we have 2 amps coming through the circuit, so 8 times 2, 16 watts total. Where's the energy coming out? At these locations here. Godspeed. I hope this helps you with solving some circuit problems.